first talk this morning is by Santiago, who will talk about homogeneities and spontaneous curvature in fluid membranes.
Thank you. Well, hello everyone. I'd like to acknowledge the invitation in this nice city. Let me to share some recent work about the inhomogeneities in spontaneous curvature in fluid membranes. So this is a picture of a cell, right? We can see a membrane that separates the exterior versus the interior. And we have a zoom, then we can see a bilayer with this kind of molecules. These molecules are phospholipids, and they are the basic structure of the bilayer. A lot of phenomena, physical phenomena, occurs here. Diffusion, yeah.
Maybe you want to share one slide so that might be easier.
Oh.
Regrese de las dos.
Oh, yeah, yeah. Mejor como estaba.
Sí, que era pantalla completa.
Sí,
¿Así?
sí. Creo que sí. Sí.
Sí, este cuadrado, no sé cómo lo... El cuadrado, puedo compartir la pantalla entera, la ventana.
Oh. Sí, sí, sí. Oh, ya entiendo. Okay.
It's coming to his laptop. But I think we're good now. Yeah.
Yeah, I think
Yes.
thank you very much. So a lot of physical phenomena like diffusion, several kind of forces and torques are acting in this membrane. So the problem is complex. But let me to focus on the part of the motivation has to be with recent experimental phenomena. For instance, in this work by these professors, they inject some kind of proteins to the membrane, then observe in these deformations of the membrane, well, this kind of shapes, a kind of dumbbell, the spheres, the form in this within this waist here. This is a recent work, and in the group of Marcus de Cerno, they study a similar simulation with this kind of phenomena. Also, a kind of protein involves the waist of the membrane to deform the surface. So let me say something about the basic of geometry. That is because in the mesoscopic scale, we can describe the surface, the membrane by a surface embedded in the three-dimensional space. Then we have the equation of the membrane. U is the parameters of the membrane, the internal parameters, and the 3D Euclidean space induces a metric on the surface. This we call GAV, well, where the GAV is the Euclidean space between the tangential vectors defined in this way, right? Of course, with this metric, we can define a covariant derivative along the surface. And to complete the basis, we have two vectors, tangential vectors, and one normal vector to the surface, right? The normal vector to the surface is defined by this formula, where we have the Levi-Civita tensor and G, the determinant of the metric, the induced metric, right? The basic equations that define the surface have to do with the Gauss equation, right? We have the covariant derivative of the tangential vectors that defines the second fundamental form, which is a symmetric tensor that describes the chain of tangent vector fields along the surface. We also have the Gauss-Garcia equation that relates the extrinsic curvature with the intrinsic curvature. The extrinsic curvature is defined by the second fundamental form, and the intrinsic curvature is the Gaussian curvature, and there is a relationship between them, right? We have the contraction and the Kodachny minority equations, where K is the traza of the second fundamental form, right? This is a cartoon of this surface with two tangential vectors in this point, the normal vector, with the surface embedded in the three-dimensional space. The way to describe the elasticity of the membrane is this theory, the Hellfish theory, ¿vale? Which involves the spontaneous curvature. The spontaneous curvature involves the asymmetries in the bilayer of the membrane, right? In this work, we consider that both the spontaneous curve and the surface tension are inhomogeneous functions defined on the surface. Normally, these are taken as a constant over the surface. The A is in this formula is the element of area. The P is the pressure jump. Sigma, the surface tension. We have the Gaussian curvature, and two phenomenologically constants, the rigidities. ¿Vale? Then the point is to obtain the functional derivative of this Hamiltonian to obtain the Euler-Lagrange equations. the equilibria, ¿vale? Then we consider the formation of the energy under infinitesimal deformations such that the derivative of the Hamiltonian, the Helfrich Hamiltonian, can be put in this as in equation 3. Only you can see only the deformation along the normal direction are involved in the Euler-Lagrange equation, right? Delta x point n. Any other deformations are included in the term that is another charge. To do these deformations, we have to obtain how the geometry deforms. For instance, to obtain how the deformation of the tangential vectors, right? We have to take, after all, this is a derivative. Then we have to conmuter this derivative and expand this deformation as these linear combinations along the tangential surface and along the normal vector, right? We have the tangential deformations and normal deformations as well. Then, in the Euler-Lagrange equations, only the normal deformations are important. Then, if we under an infinitesimal translation, we obtain this equation, so that because a consequence of the invariance on the translations, we obtain these equations on shell, right? Thus, on shell, of course, this formula implies that this integral is the elastic force acting along the membrane. This object is called the bending stress, and also can be as a linear combination of the tangential and the normal vectors. The tangential projections are given by this equation, right? We can see that in the second formula, we have the derivatives of the spontaneous curvature, right? If the spontaneous curvature is a constant, right, it simplifies. But in this case, we will have the spontaneous curvature as an homogeneous function on the surface. If the membrane is closed, we have to include the pressure jump on the right-hand side. And then when substituting this equation, we obtain the first one of these is only the equilibrium in the normal direction, the Euler-Lagrange equation, right? But now we have this second equation that is a relationship between the gradients of the inhomogeneous functions, sigma and spontaneous curvatures. We know that if k is a constant, implies that this is a constant. That is the density of the bending energy that includes the surface tension. But if no is a constant, then we cannot apply this formula, right? We also obtain the boundary conditions that can be right in this way, right? If the membrane has a boundary, these are the natural boundary conditions, right? If right, see if the equations, the divergence if we integrate these equations along the membrane, applies the Gauss theorem, we obtain this integral. Where along the membrane we have, for instance, a parallel of this. Then we have defined FA in this part, and L, unit vector pointed outside this region. This is the tangential vectors and the normal, right? So this L corresponds to the component of this L vector. Then, but there is a nice formula for the normal, for the unit normal along the surface. This is this divergence of this object. And we can simplify to the equation of the surface, right, times the tangential vector. Thus, this is a very nice relationship between the forces. This is a balance of the equilibrium, right? And of course, this is an integral of this equation, right? So it's a first integral of the Euler-Lagrange equations in this case. Of course, we can project the force in this way. We can project this force along the Darboux basis, along for instance, the parallel, to obtain this formulation, where in this case, these are the projections. In the longitudinal projection, we see the surface tension, and in the normal, not that in the normal force, we have the derivative of the spontaneous curvature. That's the difference with the standard formulation. And if we have a spontaneous curvature inhomogeneous along the surface, we have a contribution to the forces that modifies the shape, right? In this case, we have a new definitions of KL, right? The projection along the L, and the projection along the tangentials, this product and this derivative, right? Then, for instance, along the vertical axis, we have these equations. Only project the forces, the stress along the vertical directions, and we have this is a first integral of the Euler-Lagrange equation, right? In the case with axial symmetry, the force along the vertical direction is a constant. That is because the symmetry of translations in this direction, right? Of course, we have we have to do these projections. Let me say something a recent work about the spheres, for instance. That is the deformed spheres, right? Where R can be taken as for instance, the radius of the sphere to a sphere, and then we can write ADF with a small deformation here. Right? Then the spherical basis, and we have the Darboux, the Darboux basis. We have integration of along the parallel C, and then to obtain the force that that this region acts on the region below. Right? The induced metric. Only we can do some derivatives and obtain the induced metric, the determinant, and we can write the area element in this way, where we have this, right? We can obtain the inverse elements of the induced metric and the second fundamental form. Then we write all of this structure along the zeta directions in order to obtain the differential equations, the equilibrium equations, and then so what's the point now? Okay, let me in this equation, for instance, let me do here. This is the Euler-Lagrange equations, right? Then we can take a sphere, for instance, in this case. Then the K is a surface, but, or for instance, it's in a minimal surface. In a minimal surface, this K is equal to 0, right? Then we have an equations for the spontaneous curvature, right? Then we propose a surface and obtain the equations for the spontaneous curvature, right? That is the point here. We have the formation of the sphere and obtain the behavior of the spontaneous curvature. Then, in this case, the first result is that on the spherical surface, the only solutions, not a constant, is proportional to this cos, where the first curve in this picture. If we deform in this way the surface, the spontaneous curvature behavior is shown here. So, in the case of blades, we have this behavior for the spontaneous curvature. It's symmetric respect to the prolates, and we have this distribution of spontaneous curvature, right? We also deform in this way to dumbbells and obtain the spontaneous curvature distributions is more deep in the waist of the sphere form. So there is a not trivial forces acting as a consequence of the inhomogeneous of the spontaneous curvature. This is another case where the deformation is like a donut, how they say. This is a research in progress. I don't have every result, right? But let me to say something about the catenoid. The catenoid is nice because in this region, probably it seems like a catenoid, right? Then if we are interested in the nature of the forces acting, probably the catenoid be a good example. For instance, take the catenoid, right? It's a minimal surface. Then we have parameterized the catenoid with this curve with arc length L that is equal to 0 in the waist of the catenoid, and the corresponding radius A and radius B, LA, LB, and so on, right? This is the equation in this case. The Euler-Lagrange equation reduces to this one. This is the Helmholtz equations, and then we have to write here the Laplacian of the surface. In this case, the Laplacian of the catenoid, right? Of course, this is the Gaussian curvature of the catenoid, and this is negative, right? Then because K is a constant and 0, we have this property. And the first equation, first integral of the Euler-Lagrange equations can be right in this way, where the prime implies the derivative respect to the arc length, right? That's in this case we have taken the boundary conditions that appears for the Euler-Lagrange formulation, right? In this case, eta and gamma represent the constraints, because the surface is only is restricted to be the catenoid, right? Then, but the point here is that this eta is a constant. The first formula is the balance equations along the zeta directions. Then eta is a constant. But the second equation is the balance equations along the horizontal direction. So this is not a constant, right? That is the point that the first equation can be integrated. Of course, the solution is very easy, right? Then we have this structure with S this arc tangent, this function, right? And C, the constant here, is given in terms of the two radius of the catenoid. And E is defined this function here in terms of the radius of the catenoid is given by this. Well, an asymmetric catenoid, where the two radius are equal to R, then we have the axial force in this case. As in the swap bubbles, for instance, the vertical force is a constant, right? But in this case, it's also a constant, but the behavior is more complicated, right? For instance, the spontaneous curvature, because this function is have a zero for this value at this critical point. Thus, there is a behavior, very nice behavior, because we have two branches. For R less than the critical point, and for S greater than the critical point. Of course, we have the radial force in this way. Which, in terms of the radius of the catenoid, we have this behavior, right? It depends on the radius. If the radius is let me to advance, but we have this singularity in this critical point. In the presence of this in this term, right? So then we have a symmetric transition here. And this is the subcritical regime and the supercritical regime. In the first case, the behavior of the spontaneous curvature goes in this behavior, but after the critical point, note the spontaneous curvature behaves in this way, right? Then we have I think it's a kind of a first order phase transitions in case error, right? The vertical force in this case, for instance, let me to the A, B, and C corresponds to this A, B, and C in this case, right? We have the force. Recall that this force is a constant, but there is a critical catenoid. That is the same catenoid that with the swap bubbles, the instability, right? Then to obtain the critical catenoid, we can advance in this direction, but the force have to be very very high, right? And this is the height of the catenoid. Then you have this, you pass to this distribution, right? What no, let me say it here. This kind of catenoid. But in this case, we have the nature of the forces acting because the spontaneous curvature inhomogeneities, right? We can also deform the catenoid. Then we have our now a curve of the catenoids, but we can obtain the behavior of this regimen where the spontaneous where the curvature, the mean curvature is positive versus negative. On this curve is 0, the mean. The point, this is the critical catenoid. What we have asymptotically to advance in this direction or in this direction on the catenoidal curve. But we can also fix the radius and advance in this way and we obtain the same critical catenoid along these points, this curve. That is, the result is not only for catenoids, but the catenoidal curve is a critical curve of this region. And also the spontaneous curvature have this behavior. We have this, and this one, right? Of course, the Gaussian curvature is always negative, but in this case, the mean curvature is 0. That is because in this case, we have a catenoid exactly, right? If we fix the radius, then we have this behavior. Now we have this another behavior here, the waist of the membrane. Of course, in this case, we also have the vertical force is also very high along the critical line, right? For 2 radius, for instance, we have these numerical results. This is a recent work on this paper. And the conclusion is that the shape membrane is a catenoid on the naked, only if the spontaneous curvature is given by the analytical formula, right? Okay, this represents a strict necking condition. The consequent forces. The importance of the inhomogeneities of spontaneous curvature then have to be to account in this for the formation of the membranes. Not only the force coming for the curvature, also from the asymmetries on the membrane. Okay, in this case we have a critical point or critical catenoid, right? But of course, the problem is complex. But for instance, in this case, the spontaneous curvature is not conserved along the surface. As we see for instance, let me to say here. For instance, in this case, the spontaneous curvature is not conserved. Here, this is the sphere where the integral of the spontaneous curvature along the surface is 0. But for these cases, it's not 0. So we need a source of spontaneous curvature. So I am working with Paco Monroy, Complutense, some students at Mexico City, Tony, Adriana, Tony, idea. Thank you very much for your attention.